Good morning everyone. My name is Pranay. I'm from CSC AML section C. Today my subject matrices and calculus. My topic from the subject matrices and calculus is non-homogeneous system solutions for adaptive suspense systems in automotive engineering. And I would like to start with introduction of what is automotive engineering and how it is applied in our real world. An automotive suspension system is one of the most critical subsystems that directly influences vehicle comfort, safety, road holding performance, and overall driving experience. Traditionally, vehicles relied on passive suspension systems composed of springs, dampers, and mechanical linkages, while passive systems offer durability, low cost, and they are fundamentally limited because their stiffness and damping parameters remain constant regardless of driving conditions. However, real world driving conditions are inherently unpredictable and highly dynamic. Road contain potholes at times, pothole breakers, cracks, gravel patches, and random irregularities. Simultaneously, the vehicle mass distribution changes when passengers enter or exit, cargo is loaded, or during dynamic maneuvers like acceleration and cornering. These variations include non-homogeneous external forces which cannot be effectively handled by passive suspension mechanisms. Fundamentals of vehicle suspension dynamics. Suspension dynamics are primarily deal with the vehicle sprung mass interacts with unsprung mass. The simplest representation, the quarter car model, which captures essential vertical dynamics. In the quarter car system, two masses are interconnected through springs and shock absorbers. Sprung mass, the portion of vehicle supported by suspension. Unsprung mass, mass not supported by suspension, wheels or brakes. The three main forces govern motion is KS, suspension spring force, damping force CS, and for tire stiffness force. So the road puzzles Z R power T, Z R bracket T, and acts as non-homogeneous input to dynamic system. Unlike homogeneous systems, the presence of external forcing terms prevent an analytical simplification requiring specialized solution methods. Homogeneous versus non-homogeneous systems. Homogeneous system, no external input, mx plus cx, mx square plus cx plus kx is equal to 0. These represent ident self-direct oscillations. Non-homogeneous equation. A non-homogeneous equation includes time-dependent forcing terms. Mx square plus cx is equal to f of t into m. This accurately represents the behavior of suspension system encountering real-world road disturbances, sources of non-homogeneity, road surface, dynamic load transfer, aerodynamic downforce, actual forces, random variations. These forces do not allow a predictable or uniform pattern, creating significant complexity in suspension control design. Mathematical model of adaptive suspension. The mathematical representation for a non-homogeneous suspension is expressed using the quarter 2 DOF model. Equations for motion for sprung mass: mx zs square plus cs into zx minus zu into ks into zs minus zu is equal to f of atm, and for unsprung mass, mu zu square plus cu into zu minus zs plus ks into zu minus zs plus kt into zu minus zr is equal to minus fa into t into m. Key observation: road disturbances ZRT introduce time varying dynamics. Next, actuator force FATF in control non-homogeneous term. The equations are coupled requiring simultaneous solution. The matrices form is ZS ZU and FAT KT ZR minus FAT, and this formulation is basis for control design. Next, non-homogeneous inputs arise from measurable or stochastic phenomena, deterministic output, for example, speed breakers, sine wave, road vibrations, step disturbances, modeled mathematically as step function, ramp function, sinusoidal points, stoichiometric inputs like road, random road irregularities, power spectral density, white noise models, random vibration profiles, control induced inputs. Actuators generate forces depending on control designs. FAT is equal to importance. Precise modeling of non-homogeneous inputs is essential for accurate prediction. Solving non-homogeneous equations. ODE homogeneous equation is equal to h of t is equal to e into at into cx into h of t is equal to e power at cx ht e power atc. Particular solution. Several methods exist. Variation of parameters. Green functions approach. Laplace transform. State space numerical solvers, numerical integration methods, range Kutta's method, ODE 45 MATLAB, Adams Moulton method, finite difference methods, numerical methods are essential because the system often found non-linearities. Adaptive suspension system types, passive suspension, no external energy input, fixed damping and stiffness, simple and reliable, limited in adaptability, semi-active suspension, adjusting damping only, magnetorefforgical dampers, variable orifice hydraulic dampers, active suspension generates force using actuators, hydraulic actuators, electromagnetic actuators, electric linear motors, a predictive AI based suspension uses machine learning and sensors to predict road disturbances, control strategies for adaptive suspension, skyhook control controls damping gear to simulate an imaginary anchor point in the sky, ground hook control improves tire road contact, hybrid skyhook, ground hook, PID control, LQR control, H infinity control improves balances comfort and stability, simple but insufficient for highly dynamic systems, minimizes quadratic cost of states and inputs, robust against model uncertainties, MPC model predictive control predicts future and states optimization, actual dynamics, actuators play a major role in force generation, hydraulic actuators, electromagnetic actuators, pneumatic actuators. Important characteristics is bandwidth, power consumption, responsive time, and maximum force capacity, high performance actuators, and sensors and data acquisition, IMU sensors, wheel speed sensors, displacement sensors, road profilers, measure acceleration and angular rate, provide wheel rotation speed, measure relative motion between sprung and unsprung mass, estimate road irregularities, LiDAR, cameras, accelerometer arrays, data processing, sensor fusion techniques, combine multiple signals for accurate state estimation methods, adaptive suspension rails on unseen states such as road velocity input, tire deformation, relative damping rate. These are used for advanced observers, Kalman filter, extended Kalman filter, unscented Kalman filter, neural observers, optimal observation for linear gauge systems, handle non-linearities better for strong non-linear behaviors, leverage machine learning for real-time estimation, system architecture. A complete adaptive suspension system includes sensor layer, estimation layer, controller layer, actuation layer, feedback layer, raw data acquisition, road profile system and state system estimation, computes desired actuator forces, applies control force, ensures closed loop stability and performance, communication framework, CAN, FlexRay or automotive Ethernet for real-time transmission, computational complexity, mathematical complexity, solving 2 DOF, LQR computation, MPC optimization, real-time constraints, typically suspension update frequency 500 Hz to 2000 Hz. This requires fast microcontrollers and efficient algorithms. Memory requirements, store matrices for control, buffer sensor data, logging for diagnostics, real-time constraint, dictate computational strategy. Advantages and engineering benefits, comfort improvements, reduction of vertical acceleration, less vibration to passengers, safety enhancements, increased tire road, improved braking stability, better concerning performance benefits, reduced to body rolls, enhanced high speed stability, system advantage, adaptability to various environments, lower fatigue structural, superior ride even in rough terrains, non-conclusive conclusion is non-homogeneous equations offer a powerful mathematical framework for modeling real-world suspected dynamics. Their incorporation into adaptive sensation enables vehicles to achieve high levels of comfort like techniques like LQR, H infinity, MPC by handwidth and intelligent. Many of these factors help us as vehicle modes autonomy. It helps us to get a good pivotal role. And with this, I would like to conclude my topic and I thank each and everyone for giving me this topic. Thank you once again.